Good morning everyone. I am Dr. Charu Agarwal. I am working as the assistant professor in the Department of the Computer Science and Engineering in the Ajay Kumar Garg Engineering College, Ghaziabad. Today I am here to discuss the topic decision tree learning in the machine learning technique subject KCS 055, which is the part of the unit 3. So we need to be here to learn what is actually the decision tree. Decision tree is a method of approximating the discrete value target functions. Discrete value target function are basically we call for the classification problems. We can do the classification and regression both with the use of the decision tree learning, but generally we use the decision tree learning for the classification problems. With the decision tree, the learned function can be represented by this. A learned decision tree can also be represented as a set of the if then else rules. Decision tree learning is actually one of the most widely used and practical method for the inductive inference. Inductive inference means we can do the inferencing for the unseen instances based on the data that is available to us for the training. It is one of the robust technique for the noisy data, and it is capable of learning the disjunctive expressions. Decision tree method searches a completely expressive hypothesis. It actually avoids the difficulties of restricted hypothesis spaces. Its inductive bias is a preference for small trees over the larger trees. We will discuss in detail what is the inductive bias later on this series. The decision tree algorithm, we have the number of the decision tree algorithms such as the ID3, C4.5, and which are very popular inductive inference algorithms, and they are successfully applied to many learning tasks also. When we go for an algorithm for the decision tree, we can see we will have a answer like this, in which we have a root node, we have the internal nodes also, and the edges from the root node to the internal nodes or from the internal nodes to the leaf nodes, they are labeled with the values of the attributes. So in the internal nodes, all the internal nodes we have the attribute values, and on the leaf node we have the target values. So these are the actually the target values, sorry, this is the target value and these are the attribute values actually. So when the question arises, now when to consider the decision trees? Instances are expressed when the instances are represented by the attribute value pairs. Means we have the attributes and along with that we have the values of that particular attributes. So a fixed set of the attributes are there, and the attributes take a small number of the disjoint possible values. Second, the target function has discrete output values, means the classification problem. Decision tree learning is appropriate for the Boolean classifications, means in which we will have the two classes for the classification, but it easily extends to learning function with more than two possible output values also. Disjunctive descriptions may be required in this case. So decision tree naturally represent the distinctive expressions also. We will see later on how we can represent the distinctive descriptions with the help of the decision tree. The training data may contain error also. So when we have a training data that may contain the error, in that case also we can use the decision tree. Decision tree learning methods are robust to errors, both errors in the classification of training examples and errors in the attribute values that describe these examples. In that case also we can apply the decision tree algorithm for that. The training data may contain the missing attribute value. So if there is a case in which we have the training data in which for some of the attribute values, for some of the instances the attribute values are missing, in that case also we can have the decision tree, we can apply the decision tree. So decision tree method can be used even when some training examples have unknown values. For some of the training examples, for some of the instances the attribute value is missing, in that case also we can apply the decision tree algorithm. So these are the 5 scenarios in which we can use the decision tree along with the normal training data that is available to us. This is one of the example of the decision tree suppose the question that we need to answer here is, should I accept a job offer? So what are the conditions? What are the conditions that we need to satisfy to reach to the final decision? To reach to the final decision, a binary classification, whether we need to accept the offer or we need to decline the offer. So the person can accept the offer or decline the offer when the salary is at least the $50,000. So first the person choose that, find out that whether the salary is greater than $50,000 or less than the $50,000. So this can be treated as the root node. Okay, so when the salary is less than the $50,000, so when it is less than this, in no case the person declines the offer. But in the case if the salary is greater than the $50,000, then the person can look for the other attribute value, other condition. What is that for communicating to the office, it takes more than 1 hour or less than 1 hour. If it is taking more than 1 hour, yes, it is take more than 1 hour, then the person decline the offer. Then it is searching, and if in the case it takes less than 1 hour, then it searches for the third condition, whether it offers the free coffee or not. If the job location offers the free coffee, yes, then the person accept the offer, and if the company offers no coffee, no free coffee, then the person declines the offer. So this is the way in which we can explore the condition one by one. So here we can see the main condition is that whether the salary is greater than $50,000 or equal to $50,000. So if the salary is the main point here, if the salary is less than $50,000, then the person will not check for the other attribute values, it just declines the offer. So you can see here it is a binary classification problem in which there can be the two outputs only, one is accept the offer and one is decline the offer. And so we start from the root node and we move towards to the leaf node one by one by exploring the different attribute values. So we can see that a decision tree is a tree where each node represents a feature, means where each of the internal node actually represent a feature. Feature means the attribute of the training data which is available in the training data. Each link means this whole link from one node to the second node, from second internal node to the third internal node, and from the internal node to the leaf node. Each link is known as a branch which represents a decision rule, and the leaf node represents the outcome of the decision, outcome of the problem. So we can see that we need to move from here to here. So it can also be represented as an if then else rule. Now if salary is at least $50,000, if it is the condition is yes, then we check for the other condition. If communicate more than 1 hour, yes, then decline the offer. If it is no, then go for the offers free coffee or not. So in this way, one by one, the if else conditions are can be elaborated here, can be explored here. So a decision tree is a tree where each node represents a feature, each link represents a decision rule, and each leaf node represents an outcome. So a decision tree which is according to your syllabus also, the one example given in your book also. So in that particular we will do all the steps one by one. We go for that how we actually build a decision tree. For that we start with the root node and we move towards to the leaf node. So this is one more example that actually come out as the output after executing the decision tree algorithm. So what here we need to learn next, that how we actually build such kind of the decision tree. What is the algorithm actually to build this decision tree? So here we can see that what is the root node? Root node is the outlook. The outlook is an attribute. This particular outlook attribute can take 3 of the values: sunny, overcast and rain. And the second attribute value is the humidity, and one more attribute value is there in this particular decision tree, that is the wind. So wind can take 2 values, strong and weak. Humidity can take the 2 values, high and normal, and it is a binary classification problem. We can have only at the leaf node no value and the yes value. So at the leaf node we can have the yes or no, only the 2 values. So it is a binary classification problem, and in this, so you can easily see from this that that the branches which are coming out from any of the internal node, they are labeled with the values that can be go for that particular attribute value. Here wind is an attribute value, what are the values can be taken for the wind? Strong, weak. What are the values can be taken for the humidity? High, normal. What are the values can be taken for the outlook attribute? Sunny, overcast and rain. So if we need to execute, if we need to take any decision with the help of this decision tree, we can see that we first need to check the outlook. So what is the attribute which is at the root node is the most important attribute. So we need to understand this point, that the attribute which is at the root node this one is the most important one. So first we need to take the value of the outlook attribute for any instance. So if suppose we want to do the inductive inferencing, we have some instance given to us and we need to find out whether the answer for that particular instance is yes or no. In that case we need to start with the root node. The root node is having the attribute outlook. So the outlook can take any of the values sunny, overcast and rain. So we need to see in the test instance whether the outlook value is sunny, overcast or rain. If suppose for example outlook attribute have the value overcast, in that case we can directly give the answer as yes. We can directly classify that particular value as yes. If suppose outlook equal to sunny, then we need to follow this particular path. In that case we need to find out the value of the humidity attribute. If the humidity value is equal to normal, then we can give the answer as yes. If the humidity value is high, then we can give the answer as no. So in this way we can move from the root to the leaf nodes and we can classify that particular test instance into one of the classes. So an instance is classified by starting at the root node of the tree, testing of the attribute specified by this node, then moving down the tree branch corresponding to the value of the attribute in the given example, means in the test example. This process is repeated for the subtree rooted at the new node. So we can easily see from this diagram. This diagram is actually more in the elaborated form, that we can see that the attribute which is placed at the root node is the attribute. Here on the edges the attribute values are listed and the leaf nodes are the output values. In the similar way, this is a general form of the decision tree in which at the internal node we have some of the attribute of the training data. The edges are labeled with the attribute values and the leaves are labeled with the output values. So we need to generate from the training data such kind of the tree which will help us to make the decisions. Okay, so a decision tree represent a disjunction of conjunctions of constraints. Disjunction of conjunction of constraints. Actually conjunction is known as and the disjunction is known as or operator. You have already studied in the discrete that the conjunction is conjunction meaning is the and operator, disjunction is the other name for the or operator. So a decision tree can be represented as the or of and of constraint on the attribute values of instances. Each path from the tree root to the leaf corresponds to a conjunction of attribute test and the tree itself to a disjunction of these conjunctions. Okay, so each path from the tree root to the leaf corresponds to a conjunction of attribute test and the tree itself to a disjunction of these conjunctions. So we can see that if we for this particular tree, if we need to give we need to find out the rules for the yes, for the answer yes, then what we can say, what are the different combinations here. The first from this particular path, outlook equal to sunny, if outlook equal to sunny and humidity equal to normal. Okay, so you can see that if outlook equal to sunny and humidity equal to normal, then your answer is yes. So you can see here that outlook equal to sunny and this and is actually known as the conjunction and humidity equal to normal. So your answer is yes. So this is one condition. Now the second condition is outlook equal to overcast. If outlook equal to overcast, then we also have the answer as yes. So the second condition is outlook equal to overcast, then also we have the answer yes. Now the third is if outlook equal to rain and wind equal to weak, then we also have the answer yes. So outlook equal to rain and wind equal to weak. In that case we also have the answer yes. So there are the three possible conditions in which we can classify the data into the yes class. So these three classes can be odd. So in these three conditions, these three rules can be odd. So this OR operator is known as the disjunction. So this is the disjunction of conjunction. So outlook equal to sunny and humidity equal to normal, or outlook equal to overcast, or outlook equal to rain and wind equal to weak. In that case we also have the answer yes. So in this way we can represent a decision tree as a disjunction of conjunction of constraints also. Now let's do some questions that given the decision tree, now we need to find out the decision tree to represent the following Boolean functions. Suppose the first function we need to represent with the decision tree is A and negation of B, or you can say A conjunction negation of B. So for this Boolean expression what we need to do, we need to build the decision tree. So how this can be represented like this? For this particular function, to represent this particular function with the help of the decision tree, what we need to do, we can easily make the decision tree if we write it with the form of the if then else form. So we can see that if A is equal to true, then if A is equal to true, then it is A and negation of B. So if A is true and B is false, then yes, else the answer is no. So we can see that here the operator is AND. So the AND operator give the answer yes only when both the conditions are true. If any of the condition is false, in that case we have the answer as no. So a decision tree can be formed like this. If A is false, then your answer is no. Then we need to check now if A is true. If A is true and B is true, then your answer is no. If A is true and B is false, in only that case our answer is yes. Why? Because here we are having negation of B. So in this case, if you can go for the truth table, you can see that so if the F is this one, in that case we need to have the B complement. So B complement is 1, 1, 0. So the answer of AND is 0. Here 1 complement is equal to 0. So 0, 0, answer is here 0. 0 complement of B is equal to 1. So 1, 1, answer is 1. B complement of B is equal to 0. So in that case the answer is also 0. So in this case you can see that we can get the answer of 1 only in this particular condition, when A is true and B is false. So when A is true, B is false, we have the answer as yes, otherwise the answer is as 0. So in the similar way, what you can do, you can draw the decision tree for the remaining of the Boolean functions, that F is equal to A or B and C. So here if A is true, then we have the answer yes. If B is equal to true and C equal to true, then yes, else otherwise we have the answer no. So in the similar way we can draw the decision tree for this problem also. And we can also draw the decision tree for the next function F is equal to A XOR B. We know that A XOR B can be written as A B complement or plus A complement B. So this can be written in this form, and in this if else form we can write this particular expression and we can draw the decision tree here. So for this for the decision tree of the if then else rules form can be represented like this. We can write the disjunction of conjunction form of the decision tree in the form of the if then else rule form like this. Now we need to understand, after having understanding of what is actually the decision tree, what are the nodes, what attributes are represented by the internal nodes, what actually we need to represent by the leaf node, what are the label that we need to give to the branches or to the links. After that we need to go for how to design a decision tree, how to construct a decision tree. So there are the number of the algorithms through which we can have the decision tree, we can construct the decision tree. The one is the CART algorithm, the other one is the ID3 algorithm. Here we give main focus to the ID3 algorithm. Why? Because ID3 algorithm is in the syllabus and it is the most widely used algorithm for building a decision tree. Now here what we use in the ID3 is the entropy function and the information gain. If somewhere you have the question like where we use the Gini index in which algorithm, then you can easily answer that it is used in the CART algorithm, and the entropy function and the information gain function is used in the ID3 algorithm. Now what is this ID3? ID3 is actually stands for the Iterative Dichotomiser 3. ID3 stands for the Iterative Dichotomiser 3 and is named such because the algorithms iteratively means repeatedly dichotomizes. Dichotomizes means divides features into the two or more groups at each step. So here we are having in the ID3 two words, one is the iterative, one is the dichotomizer. Iteratively means repeatedly and dichotomizers means divides. So this particular algorithm repeatedly divides the features, repeatedly divides the data into the two or more groups at each step. So that is why this algorithm given as the name as ID3, because it is repeatedly divide at each step the whole training data into the two or more groups based on the attributes values. This ID3 is actually invented by the Ross Quinlan in 1975. ID3 uses a top-down greedy approach to build a decision tree. In simple words, the top-down approach means that we start building the tree from the top, means from the root node, and the greedy approach means that at each iteration we select the best feature at the present moment to create a node. So it applies, so it is a top-down greedy approach. Starting from the root we build the tree to the leaf node, and the greedy approach is that at every moment it select the best feature. Most generally ID3 is only used for the classification problem with nominal features only. What are the main steps in general form for the ID3 algorithm? It calculates the information gain of each feature considering that all rows don't belong to the same class. Split the data set S into the subset using the feature for which the information gain is maximum. It makes the decision tree node using the feature with the maximum information gain. So the most important point that we need to remember here, the maximum information gain. The node which has the maximum information gain, that is taken by the decision tree algorithm, this ID3 algorithm. If all the rows belongs to the same class, make the current node as the leaf node with the class as it label. Repeat for the remaining features until we run out of all the features or the decision tree has all leaf nodes. Now the question arises that in the previous slide we see that the ID3 algorithm select the best attribute. Now the question is which attribute is actually the best one? There in the training data we can have a number of the attribute. Now we need to select which attribute is best. So we would like to select the attribute that is the most useful for classifying examples. Information gain measure actually tell us how well a given attribute separates the training examples according to their target classification. ID3 uses this information gain measure to select among the candidate attribute at each step while growing the tree. So at each step we need to measure the information gain to select the best feature. In order to define the information gain precisely, we use a commonly used we use a measure which is commonly used in information theory, which is known as entropy. So here in the ID3 algorithm, two formulas or two measures are very important. One is the information gain and second is the entropy. Basically we use the entropy to ultimately calculate the information gain of the attribute. Here entropy actually characterizes the impurity of an attribute collection of examples, or you can say it's a measure of the impurity or purity of an arbitrary collection of examples. What is entropy in our context? We have given a collection S which contains, if it is a binary classification some problem, then some positive examples and some negative examples of the target concept. The entropy of S relative to this Boolean classification, yes or no, is given by this particular formula, that entropy is equal to minus all the positive number of the positive example log base 2 of the positive examples minus number of the negative examples log base 2 of the negative examples. So, where this number of the positive example is the proportion of the positive examples in S, and this is showing the proportion of the negative examples in S. So, in all calculation in entropy we define log base this to be 0 log 0 to be 0. Now, what is the information gain measure here? Information gain is simply the expected reduction in entropy which is caused by partitioning the examples according to the attribute. More precisely, the information gain S comma A, where S is the set of the example and A is the attribute, is given by this particular this formula. And we need to calculate the entropy of the whole data set, and minus we calculate the entropy of the each and every attribute, and we subtract the entropy of the attribute from the entropy of the data set to find out the gain of that particular attribute, where values of A is the set of all possible values for attribute A, and SV is actually denoting the subset of S for which attribute A has value V, that is denoting by this particular expression. So, this is the entropy of the whole data set, and this is the entropy of S after the partition. So, gain S comma A is the expected reduction in entropy which is caused by knowing the value of the attribute A. Gain S comma A is the information provided about the target and the action value given the value of some other attribute A. The value of gain S comma A is the number of the bits saved when encoding the target of the attribute member of S by knowing the value of the attribute A. So, students, this is all about the entropy and the information gain, and in the next lecture of this series we will study in detail the ID3 algorithm. What actually the ID3 algorithm? In this particular lecture we have understood that what is actually the decision tree, what is the structure of the decision tree, what are the algorithms in, and the measures that we use in that algorithm, the information gain and the entropy. In the next lecture we will discuss the ID3 algorithm in detail, and we also go for an example, and for a data set we will construct a particular decision tree for the training data set. Okay, thank you so much.